We're going to begin the study guide for Chapter 2. Remember that there will be a homework sheet for the student that looks like the study guide, and then there's a test that looks like the homework. And so this is a time that the teacher can review the student, and then later on the homework is the time for that student to dig it out, work through it on their own, have the book and the study guide to compare with, and then take the test on their own. So, statement. All points are collinear. All points are collinear. If we want to write that in if-then form, then we're going to take the first part of that point. We're going to try to put an if in there, but we have to lock it down to being one single point. And we're going to use something like it, or he, or she. This is not a human, so obviously we would say it. So we need an if, and we need an it. If it is a point, then it is, now see, that didn't work, did it? Because collinear, really we have to be talking about 3 points or more, right? If we go back to our properties. So we get to writing this, and then we get to going, hey, there's more to this collinear thing. So because of that definition, I need to go back, and if I'm going to disprove it later, I need to interject more into it. So we're going to have to say if they are points, then they are collinear. See? So the first time we did that, it was like with a bird. If it is a bird, or if it is this, or if it is that. But see, when you have a definition that sometimes requires more than one, we have to be plural, not singular. So we're going to say if they are points. See, this is going to make better sense to the story. Then they are collinear. Okay, so we have to be a little bit mindful of English vocabulary and geometry definitions to be able to properly change these to if-then statements. Remember that the if part of the if-then statement is the hypothesis. It's the if part without the if, and so the hypothesis is they are points. And the conclusion is the then part without the then, and so the conclusion is they are collinear. The converse, to write the converse, we switch the if and the then. We're still going to have if and then where they were, so we're really not switching the if and the then, we're switching the hypotheses and conclusion. We're going to let the hypotheses become the conclusion, and the conclusion become the hypotheses. So now we say if they are collinear, then they are points. To write a biconditional, we would go back to the original if-then form. We would drop the if and drop the then and put if and only if where the then was. So it would become they are points if and only if they are collinear. Now, in reality, we're not supposed to write a biconditional because to be able to write a biconditional, the statement and its converse must both be true. Well, in this case, neither one of them are true. A counterexample to the original statement that says if they are points, then they are collinear could be given with a diagram of three non-collinear points or just non-collinear points. So you could put in words non-collinear points as a counterexample, or you could draw a picture to show non-collinear points, which would be a counterexample. Again, a biconditional would say they are points if and only if they are collinear, but since the statement and its converse are not both true, then we really aren't supposed to write a biconditional. We just needed you to be able to practice writing one. Okay? The next little section is justifying properties from algebra. And when we justify properties from algebra, we're going to remember that the first one is always given. We say, well, where did this information come from? Well, it's the problem that we started with. It's the given problem. After that, what we want to do is compare the statement that we're on with the statements above it and see how they're alike and how they're different and think mathematically about what it would take to change from the one we have to the new one. Well, when we look at the comparison, there's a 20 and an equal and a minus 4 and an equal and a 20. So if we compare those, we can see that what happened was this 2x disappeared. This 12x disappeared. And if we think algebraically, we would think about the bottom of the order of operations horseshoe on page 33 of my Algebra 1 textbook, which says we're going to get the variable that we're isolating on one side of the equal sign, remembering to change the sign when we cross over. And so a 12x must have been subtracted from both sides. So this is a result of the subtraction property of equality. And now we're looking for a reason for this one. And so we compare it to the statement above it. We got a 4x and an equal and a 4x and an equal. And you can see that the minus 4 disappeared. And as we think through that order of operations, we would be thinking, okay, I've gotten the variable that I'm isolating on one side. Now it's time to undo. I've got multiplication and subtraction. I would undo subtraction by addition. So I would add 4 to both sides. So this is a result of having added 4 to both sides. That is the addition property of equality. Any questions on that? And now we need a reason for this statement. If we continue the concept of undoing, then you would know that we would need to undo multiplication by division. So this is a result of having divided both sides by 4. So it is a result of the division property of equality. Any questions there? Okay. People get these mixed up. One of them is reflexive. One of them is symmetric. Remember, reflexive is like looking in a mirror. It's equal to itself. So what's over here is what's over here. Now that's kind of tricky if we say look in a mirror, I know, because it kind of flips when you look in the mirror. But anyway, equal to itself, reflexive property. Symmetric property is when you flip the equation around. What was on the left goes to the right, and what was on the right goes to the left. So the B was on the right, now it's on the left. The A was on the left, now it's on the right. We flip the equation around, that's symmetric. Any questions on that? Angle 5 and 6, if we draw them, we see that they're angles across from each other when two lines intersect. We call those vertical angles, so we can say they're equal by the vertical angle theorem, which just we simply say vertical angles are equal. Vertical angles are equal. If segment BD bisects segment AC, the bisector of a segment is a line, segment, ray, or plane that intersects a segment at its midpoint. That's the official definition. But what we wanted in this text is what you get out of it. What we get out of it is two equal segments. So if segment BD bisects segment AC, then we can conclude that segment AD is equal to segment CD. With the reason, there's the word, and there's the what we get out of it. And so we say definition of whatever that word was, bisector of a segment. Next statement, it says that BD is perpendicular to AC. Perpendicular lines are two lines that intersect to form equal adjacent 90-degree angles. That was kind of a big one on the right, a little one on the left. Sorry about that. Now, not only does it say that they are 90, that angle 3 is 90, and angle 4 is 90, but we can also conclude that angle 3 is equal to angle 4. So we can conclude that angle 3 is equal to angle 4, and that is definition of perpendicular. From the definition, we get that those angles are equal, or we can get that individually those angles are 90. Ray BD bisects angle ABC. Ray BD bisects angle ABC. A bisector is a ray that divides an angle into two equal adjacent angles. So what we get out of that is that angle 1 is equal to angle 2. There's the word angle bisector. There's what we get out of it. We have the word in what we get out of it. And so we say definition of an angle bisector. D is the midpoint of AC. The midpoint of a segment is the point that divides a segment into two equal segments. What do we get out of a midpoint? Two equal segments. But that's what the definition says. There was a theorem, though, that we used to prove that one of those little ones is half of the whole big thing, and the other little one is also half of the whole big thing. And that was a theorem that we proved using the definition. And so when we say that one of the little ones, like AD, is half of the whole big thing, I'll clean it up so we can see. Half of it, one of the little ones, AD, is half of the whole big thing, AC. That's not the definition of a midpoint. The definition says the two little pieces are equal. This is the midpoint theorem. Remember that the midpoint theorem says that one of the little ones is half of the whole big thing. Any questions on that sequence of problems? Okay. Number 18, what we're using here is concepts that we've studied as in vertical angles are equal. If this angle is 60, then the angle vertical to it is 60. Angle 1 is vertical to it, so angle 1, whoops, I'm sorry, got on the wrong spot there. Then angle 1 must be the same measure, 60 degrees. So now in the diagram we have that is 60 and this is 60. Now we know that a straight angle is 180 degrees. So angle 1 and 2 go together to make 180 degrees. So we can say that they are a linear pair or that they are supplementary. To get angle 2, we could take 180 degrees minus 60 degrees, and we get that angle 2 is 120 degrees. Angle 3 is vertical to angle 2. That means that angle 2 is equal to angle 3 because vertical angles are equal. So angle 3 would also be 120 degrees. The next question says a complement of angle 1. Complementary angles are two angles whose measures have the sum of 90. Angle 1 is 60. A complement of 60 then would be 90 minus 60, which is 30 degrees. And so a complement of angle 1 would be a 30-degree angle. Supplementary angles are two angles whose measures have the sum of 180. If we want a supplement of angle 1, and angle 1 is 60, then to get a supplement of angle 1, we would take 180 minus angle 1, which is 60, and we would get 120 degrees. So a supplement of angle 1 would be a 120-degree angle. Any questions on that? Okay. Number 23. When you do word problems, if you follow from the Algebra 1 text that I wrote, again, it can be found at www.dballardproductions.com. Page 37 and 38 of that text is turning word sentences into mathematical equations. Page 40 is steps in doing a word problem, and that's where we talk about characters and word sentences. Complementary and supplementary are on page 52 of that text, and then we've dealt with them here in the geometry book. Now, what we would do on page 40 of the Algebra 1 text, we would say it says a supplement is 3 times as large as its complement. And so what we would do is would say, well, that's a comparison between two characters. Supplement S is, see, we need the characters, and the verb, and anything that means add, subtract, multiply, or divide. So all we need is supplement S is 3 times, that means multiply. As large as we don't need, we do need the other character, complement C. S is 3 times C, that's all we need. And then it says find the measure of each angle, so that must be the question, and so all we have is one word sentence. We have the characters supplement, complement, but it says of an angle. Now, we know with 3 variables, you would have to have 3 word sentences unless you can name them in terms of the same variable. Page 42 in the algebra text says to be able to do the order of operations, you can only have one variable or one name. If you have more than one, you must name one in terms of the other and use substitution, which requires more than one equation, or use special rules to name each one in terms of the same variable. And we use things like consecutive integers, x plus 1, x plus 2. Consecutive even or odds, x plus 2, x plus 4. Or over on page 52, we use things in a ratio where we multiplied each member of the ratio by x. What we're going to do here is kind of branch off of this concept of what would a complement or supplement of something be. And think about what would a complement of x be or a supplement of x be. If we let the angle be x, then to find a supplement, we do what we just did a while ago. We subtract the angle from 180 and we have its supplement. To find its complement, we subtract the angle from 90 and we have its complement. And now all of a sudden, we have 2 different characters, but they've been assigned in terms of the same variable. So again, page 42 says to be able to do the order of operations, you can only have one variable or one name. If you have more than one, you must name one in terms of the other and substitute or use special rules to name them in terms of the same variable. So we've been able to, with some rules of complementary and supplementary, name them both in terms of the same angle x. So in place of supplement, we're going to put 180 minus x. Is means equal. 3 times means multiply. And in place of complement, we're going to put 90 minus x. Now this is 3 times 90 minus x. Now rule 2, page 37 in the algebra text says, if you multiply something to or divide something by a sum or difference, you have to put that sum or difference in parentheses. Distributive property on page 171 of the algebra text said it this way. You can only distribute onto a one lesser operation. Now, when we get ready to distribute, we have to remember you can only distribute onto a one lesser operation, but we said if any higher operation like multiplication or division is happening to a lower operation like addition subtraction, that lower operation has to be put in parentheses. Now, the order of operations horseshoe is on page 33 of the algebra text. And here's how we do it. It says, is there anything we can do to simplify either side in the order? Please excuse my dear Aunt Sally. Looking for distributive property, and we find distributive right there. So on the right side, we're going to go ahead and distribute. 3 times 90 is 270. 3 times negative x is negative 3x. So we'll go back to the beginning of the order of operations horseshoe and say, is there anything that we can do to simplify? In the order, please excuse my dear Aunt Sally. Looking for distributive and combining like terms, and there's not. There's nothing we can do to simplify, so that takes us to the bottom of the horseshoe, and it's got some words in parentheses on the bottom of page 33, and it says this. Get the variable that you're isolating. See, we've got x's on both sides. Get the variable you're isolating on one side of the equal sign second, remembering to change the sign when you cross over. And so we're going to have 180. We've got a negative x and a positive 3x. The signs are different. When you add or subtract with different signs, you subtract. 3 minus the understood 1 is 2x. And you take the larger sign, which is positive, and we'll add to our list over here sign rules. Sign rules are on page 18. So we have 180 plus 2x is equal to 270. We've done all we can do to simplify. We've gotten the variable we're isolating on one side, so now it's time to undo. We're going to undo in the reverse order. Sally, Aunt Dear, my excuse, please. In using inverse properties, the 2 that's crammed on the x is being multiplied, and that 180 is being added on. This gives some students problems sometimes in Algebra 1. Added on, I was writing problems. So we're going to undo what's added on before we undo what's multiplied because we reverse the order. So we're going to undo addition by subtraction. We subtract 180 from both sides. We're going to get 2x is equal to 270 minus 180 is 90. Now we're going to undo multiplication by division, and we get x is equal to 45. Now, on page 40, when we did word problems, the last thing it says is to make sure that the answer makes sense to the story. And we said that means we need to read the question again and make sure we're answering what it asked for. It asks us to find the measure of the angle. The angle is x. And so we must have done it correctly. Well, we found the angle x. We could plug it back in to see if we did it correctly. Any questions on that? Okay. Number 24. If AB is perpendicular to CD, we got to go to the definition. Perpendicular lines form equal adjacent 90-degree angles. So we can say that angle 1 is equal to 90 degrees. If we had to give a reason, it would be definition of perpendicular. This says name 2 pairs of supplementary angles. We know that angle 1 and 2 go together to make a straight angle, which is 180. We know that they are a linear pair. The sum of their measures is 180, so we can conclude that they're supplementary. Supplementary angles are two angles whose measures have the sum of 180. There's another place where we have two adjacent angles whose exterior sides make a line, angle 3 and 4. That's the definition of a linear pair. A linear pair add up to 180 because a straight angle is 180. If two angles measures have the sum of 180, we can also say that they are supplementary. So we can say that angle 3 and angle 4 are supplementary angles. If we knew that angle 1 was equal to angle 4, then we could reach the conclusion that angle 2 was equal to angle 3 and justify that with the reason supplements of equal angles are equal. That's my abbreviation for angles in the middle of all of that. Okay? Complementary angles. Complementary angles are two angles whose measures have the sum of 90. Angle 1 and 2 go together to make that right angle. Therefore, we know that they're complementary. Angle 5 and 6 go together to make this right angle over here on the right side. Since the sum of their measures is 90, we can say that angle 5 and 6 are complementary. If we knew that angle 2 was equal to angle 5, then we could conclude that angle 1 was equal to angle 6 because complements of equal angles are equal. Any questions on that section? Okay. We're going to give reasons in a proof. If we are, then we need to create a note section. We're going to write the given proof, put the statements on the left, reasons on the right, draw the diagrams, create a note section. That's done. We then would take what we're given, mark it in the diagram, write statements and reasons derived from the markings in the note section. Given that AO is perpendicular to OC, we reach the conclusion that that angle right there is 90 degrees. So we can say that angle AOC is equal to 90 degrees. And the reason we can say that is we read that and we heard that word perpendicular. So we have the word and what we get out of it. And so we say definition of perpendicular. And we know that if we're going to say definition of, then we have to have the word and the what we get out of it. And so we need the word in the statements before the reason definition of. And so we need to put that word in and the reason for it was given. So we took what we were given, we marked it in the diagram, we wrote statements and reasons derived from the markings in the notes section. And so now we're going to start giving reasons in a proof. Remember, to give reasons in a proof, we look first at the given. We look second in the diagram. We look in the given first because if it's given, why did we spend time looking everywhere else? It's right there. If it's in the diagram, it would only be things like definition of a straight angle, it would be things like angle addition or segment addition, angle subtraction, segment subtraction. Vertical angles are equal, things that we visually see. And if you visually see them, you're not going to find them in the statements above, so you'd be wasting a lot of time looking there. If it's not in those two more obvious places, then we would go digging into the statements above.